Hello, this video is for Stat 110 and includes a discussion of the study guide for exam number 2 for the spring 2024 semester. Exam number 2 is going to cover sections 3.1 through 3.3, sections 4.1 through 4.4, and also section 5.1. This semester, your exam number 2 is going to be 80 points with an in-class part, and we are going to have a 20-point take-home part as well. Okay, let's go ahead and talk about the study guide itself. All right, the first question has to do with a table that's presented to us, and it is asking about, or that's showing, whether or not adolescent is adopted and whether or not they had attempted suicide. So here the p-value for this analysis is set at 0.0001, so they tell us that. This p-value is less than 0.05, so we do have enough evidence for the research question. So the correct response here is one that starts out with that we do have enough evidence, and then we just follow along with the research question here. And then make sure and include the p-value at the end. So if you have to write one of these out, make sure that you're including that p-value at the end there. So because the p-value here is less than 0.05, then we do have enough evidence. We have a relative risk calculation for that data up above. The relative risk calculation is going to be using these totals here. So to compute the relative risk ratios or the risk differences, we're going to look at the row percentages. And those row percentages are going to be 47 divided by 692 here. Sorry about that. 47 divided by 692 is going to be one of those row percentages, and then the other is going to be 9 divided by 540 here. So the relative risk ratios or relative risk differences are going to use these totals. So it's the one... Yep, it's going to be A here, 47, 692, and 9 divided by 540. Okay, when we do odds ratios now, odds ratios do not use the totals. Okay, so when you're looking at odds ratios, it does not use these numbers, nor do odds use these numbers. It is a straight up comparison of the numbers that we have provided here. So an odds calculation is going to be 47 divided by 645, and then 9 divided by 539. So that is going to be C. There is our answer for that one. Okay, we had questions about this in class today, so let's talk about number 4. If I have the statement blank times more likely, that is telling us that we are doing a ratio. Okay, so it's either going to be an odds ratio or a relative risk ratio. Now, how do I know which of those two it is? If I'm interpreting an odds ratio, then I have to say odds in my sentence. Okay, so I don't have odds here anywhere, so this would not be an interpretation for an odds ratio. So the answer there is going to be D. Okay, here's a question out of chapter 3 is where this is coming from. Here's data for attendance, okay, or number of absences, across the days of the week. And we're asking, are students more likely to be skipping on certain days compared to others? If we are carrying out a chi-square goodness of fit test, when we are setting up those when we're setting up the test, we're going to assume that the students are all equally likely to skip on any given day. Okay, so that's how those expecteds are computed, is under the assumption that everything is equally likely. Or oftentimes I'd say no difference. Okay, so that is going to be, A is going to be our answer there. When we're doing the expected number, and it's under a situation of all equally likely, there's 1, 2, 3, 4, 5 days, and I think the total number of absences is 100. So if you take just 1/5 of 100, then that's where we get the 20 there. Okay, let's keep going forward here. This is a p-value question, really. It's very similar to ones that we've had in the previous exam. What is this p-value really measuring? Well, the p-value measures how extreme the data value or the data is, okay, under the situation of no difference. So here, there is a 15% chance of observing a result as extreme or at least as extreme as the outcome obtained from the data. That's definitely the interpretation of the p-value. Okay, but again, it's under the assumption that students are equally likely to skip. So we're trying to measure how extreme our data values are under this situation of equally likely. Okay, so D is going to be the answer here. C, this first part, is not how the expecteds are computed. Okay, so C is not correct. And A and B are just, those are just distractors there that aren't relevant. Here's a conclusion statement. So this one's a little bit easier because if the p-value is not less than 0.05, then I do not have enough evidence. So I'm just looking for the results do not provide enough evidence, and then I just have the research question stated there. Okay, so C is going to be the answer there. Here's a data table on, what are we looking at here? Whether or not individual owns a pet. And I have this broken out between males and females. So here's what the 100% stacked column graph looks like. In order to compute this again, we need to figure out the yes boxes, okay, are going to be, yes for male is going to be 8 divided by 30. So that's where that 26% is coming from. It's going to be 16 divided by 30 for the females. So that's where that 53% is coming from. And then obviously the two other row percentages for the no column would go here in white as I have them sketched here. So just getting comfortable with those row percentages and being able to plot those out on one of those mosaic plots or 100% stacked column graphs. Here's another expected question. Okay. How do I calculate the expected for this situation? The first thing that I need to do is get an understanding of what percent of the people are males. So to do that, I would look at 30, and then I would divide that by 60 here. So that'd be 50%, or 1/2. Right? And then I do what percent of the individuals are female. So I would do 30 divided by 60. So that's going to be 50% as well. So now what I have to do to get the expected, so if I want the expected for this cell right here, well, from my row calculation, I know that it was 50% of the 50% of the people in the study were males. So I need to take 24 times 50%, which is going to be 12. Or I got to take 24 and just cut it in half. So I'm going to end up with 12 here as my expected. I would also end up with 12 here as my expected. If I wanted the expected over here for this cell, I would need to take 50%, because that's how many percent of the people that were in the study that were male, 50% of 36. So I'd have 18 and 18 here. Now, one thing that's unique about this example here is that the number of males and females in the study are the same. So the expecteds are going to be the same between the males and the females. The ones we did in class, this might have been a little bit higher count. So that means I have to allocate a little bit more of that 24 to this box. So let's suppose that these numbers were instead 40 and 20. So now 2/3 of the people in this study are males. 40 divided by 60. So if these were my totals, then I would have to take 24 times 0.66, or 2/3, to decide how many go here. And only 1/3 would go here. All right, so if you're looking at the notes, we did several examples where the numbers were not exactly the same. Calculating the expected requires two things. First, get the row percent, or get the percent for this row and get the percent for this row, and then you just multiply by those totals there to get those expected counts. So this one's going to be 12 and 12. Okay, a sequence of true-false questions based on these tables right here. This table right here, I have absolutely no difference. So if you were to make one of these plots here for table A, those two bars are going to be straight across from one another. So if I'm trying to test whether or not there's going to be a difference, then table A over there, or friend A, is going to have a there's no difference at all. So that's going to be a very high p-value. Not a small p-value, but a very high p-value. The data from friend A is likely to support the research question? No. Nope, that's not the case at all. This looks like data where there's no difference. The data from friend B is likely to support the research question? No, because this one's really close to what I'm seeing from friend A. They're only one off. C is definitely going to support, because if you create the 100% stacked column graph for friend C, those two boxes are going to look very, very different from one another. And if they're very different from one another, then that p-value is going to be small. All right, let's keep going here. Number 12 is just understanding a little bit about differences between studies and what that might mean. Study A, I got 40 out of 100 women dream in color, where it's only 20 out of 100 for men. Okay, and study B is 35 out of 125. Well, there's a bigger difference here in study A. So if both studies have the same number of people in it, okay, which they do here, then the one that has the biggest difference, or the bigger difference between the two, is going to have stronger evidence. So that's what we have here. For 13, the percent, okay, is the same between them. 30% women, 20% men, but study C has a lot more people. 2.5 times more people, or whatever that is. So study C is going to have more evidence. So if a study has more people in it, then you're able to get more evidence for the conclusion that you're trying to draw. Okay, there's 14. Again, the primary variable that I care about is perception here. So that is going to be my response variable. So whatever your primary variable that you're trying to compare across is your response variable. The explanatory variable or predictor variable is what creates your two buckets. So here I'd be looking at good semester and bad semester, trying to make comparisons across those, making comparisons in the perception across those. Okay, so the question would be the explanatory variable, and the perception would be the response variable. Another question just about what does it mean to have a small p-value. I'll let you guys work on that one. This one here is a little bit, I don't want to say tricky, but just takes a little bit to understand. What we did here is we measured level of lead in 2 consecutive years. So a high implies that a child has high lead levels in both years. A high-low would be they had high levels of lead in year 1, but low levels in year 2. And then a low-low would be they had low levels of lead in both years. So it's a little different way of looking at that, and it's just 3 different columns here. My buckets are how close they are to the lead pollution source. So are they real close? Or are they closest? There's my 3 different levels there. The proportion of children in the high level of lead for both years, so that's going to be the gray boxes here, high level of lead in both years, is highest for the close group. No, that's false. It's actually highest for those that live closest to the lead pollution source. The location has an impact on the low children. Low are the black boxes, and they are almost identical, straight across nearly, so that's false. A majority, over 50% of the children, had low levels of lead in year 2 of the study. So low levels in year 2, you're going to be wanting to look at the black boxes and the white boxes, because those have low in year 2. So that is true for closest, that is true for closer, that is true for close. So that's going to be a true statement. The location, close, closer, closest, has an impact on lead levels. It does, because you're seeing a different pattern here, especially in that high versus that high-low interaction there. And this is a false statement, because we're doing everything based on row percentages, so you don't have to worry about the fact that those are different numbers. You don't have to have the same number in every study, each group, to make comparisons. That's why we're doing everything with row percentages. Here's another example. This has to do with some of the stuff from Minnesota Department of Corrections. We presented some information about sex offender treatment programs, and here's just another study based on that. The bottom here are my different buckets. Are they never entered the program, or did they quit or get kicked out of the program, or did they actually complete the program? So this column over here is complete the program. We got some true falses based on these. The height of box A is computed by 282. The height of box A is going to be the never entered group, and That's no rearrest. So that's going to be 282 divided by 485. So these are row percentages in here. So that's going to be 282 divided by 485. We don't use this 629 number at all down there. Again, we're kind of looking at three different buckets here. The never entered bucket, the quit terminated bucket, and the completed bucket. What do we got here? The fact that box B is bigger than box A implies individuals. Yep, that one's fairly straightforward. This one catches students here. Box C is about twice as big as box D. So the risk difference would be about 2. That's going to be the ratio. So if I say this box is twice as big as that, that's a ratio thing. So the relative risk ratio would be 2, not the difference. The difference looks like it's about 5 percentage points. Okay. Treatment program appears to be working. Yep. This over here, those that completed the program. I had a lot more not rearrested there, so that's good. Yeah, that's okay. Okay, the last here is just some extra questions from the section from 5.1 material. Okay, so suppose the scores on an exam range from 0 to 100, the median must be 50. That is false. I could have data that looks like this, 0, oops, and then I have 75, 75, 75, 80, and then a 90 maybe. Oh, no, they range to 100, I guess. So if I do the median thing, I'm going to cross off that one, cross off that one, cross off that one, cross off that one. The median here is going to be 75. It doesn't have to be 50. Okay, so this one's false. Income data tends to be skewed to the higher values. That is true. We talked about that in class. In that case, the mean is likely to be larger than the median. This is backwards here, so that's false. The mean, the average is what gets drug up. The average measured on the same scale as the data? Yep, it is. So if I'm looking at dollars, okay, if I calculate the average of that data, the units on the average is dollars. Yep, that is true. And then a CDF plot allows you to see the entire spectrum of the data. We talked about that quite a bit on Monday, so that's true. Okay, suppose a test is given to 40 students. After grading the exams, 6 students with the lowest score did exceptionally worse. So I had 6 really low scores. Okay, 6 really low scores, and I'm going to curve them, or the teacher decides to curve them a little bit. So you think of the mean, I guess I don't have a picture in front of me, but you think of the average as a balance point. So if those lower scores are down here on the bottom, and I'm going to move them up a little bit, then my balance point has to move up because my data values are shifting up. So the average is going to increase a little bit. However, if I do that same thing with the median is not going to change. The lower data values are just going to shift up a little bit, but when I'm calculating the median for all 40 of these students, those still get crossed off, right? Like we kind of talked about in class, when we're doing the median, we cross off the lowest one, the highest one, the second lowest, the second highest, all the way down through. So those are just going to get crossed off. So the median, again, isn't going to change in a situation like this. Okay, I think that does it. So that is our study guide for exam number 2. Good luck. We'll see you Friday.